Hi team, welcome to sheet 2 or video 2 for chapter 8, which is on modelling. For this we are going to start looking at how we construct a model. Now just a bit of a reminder of kind of the rationale behind modelling and why we do it. If we think of or kind of look at a situation that's one that we will look at actually as we go through into more kind of proper mechanics, I suppose. If we have, for instance, a car towing a caravan which is accelerating along a 50-meter road. Now, what we might be interested in at this point is the forces involved. Okay, so we've got a car and a caravan, and with that car and caravan, we've got some kind of frictional force forward, which is making that car go along the road. On those wheels, we've got it on this wheel here. We've got some force forwards through the tow bar on the caravan, pulling that forwards. Now that's going to be met by some resistive force, some air resistance on the car, and also on the caravan. And so obviously the aerodynamics of those two objects will have an influence on the size of that force. We'll also have a kind of tension going against, or going in the opposite way, a kind of reaction force going from the car onto the caravan. We've obviously got the weight of the car and the weight of the caravan. We've also got reaction forces from the car to the ground and from both sets of wheels and also the wheels of the caravan. Now, as you can see from this and just from that whole description, there's lots and lots and lots of information and things going on in this diagram. Now, this isn't even everything that's happening. Okay, there's kind of the engine power we could take account of. We look at the details. We could look at the way in which the wheels are turning, the inertial forces of the wheels. All of these things will have an influence on the motion of this car and the caravan. But what we're interested in is trying to model this situation to be able to make conclusions without the need for such complexity. So constructing models, as we've kind of mentioned last video, is about simplifying a situation, and we're going to make key assumptions to do that. Now, assumptions kind of necessarily will mean that there's uncertainty and error in our calculations. There is some way in which these assumptions will mean that our calculation is not 100% accurate. What we want to do, and a good model will do this, is we want to find some balance between this uncertainty, so the uncertainty involved and the uncertainty created by the assumptions we use, and also we want to balance that with the way in which, or the ease with which we can calculate information that we're interested in. So there is some balancing point here between the uncertainty and the calculation. Now, on the screen at the moment are kind of six, I think, of probably the most important modelling assumptions that we will be using as we go through. Now, what I do, if I use pause this video now, make some notes here. There are some other modelling assumptions we may well mention, but these are the six key ones. I'm going to talk a bit about how these and what influence these will have on specific situations in a second, but please pause the video and make any notes you want to now. So you should have some good notes there. These, as we start using them more and more, will become clearer and clearer. But key thing is we're going to look at how we use these assumptions. So let's think about a situation where I've dropped a penny from the top of a wall. Okay, so we've got some penny. My model will assume that penny is a particle. Now, as you've seen, the particle will allow me to ignore air resistance. Now, what I think about when I think about this is how valid an assumption is that? Now, realistically, for a penny, it's pretty small. It's pretty the mass is fairly concentrated, and that means that any rotational effect is negligible, and as is any air resistance. We've got a really quite a small surface area there, and the speeds from if you drop it from a wall won't be such that it's going to have a serious impact on the situation. So we've got a fairly valid model there. Now, obviously, it will kind of make sense if we can model a penny as a particle. Penny is quite a small, solid object. We might be interested then, okay, fine, every time we drop something, we could model it as a particle, but we may well get into some troubles. For instance, if I drop a piece of paper from the top of a wall, okay, if I model the piece of paper as a particle in this situation, then my validity is going to be quite poor. We know from our own experience that actually a piece of paper will kind of float down to the ground, that means that realistically my model was not going to be as strong as my original example using a penny. So that kind of starts to talk about some of the reasons or some of the issues with validity, and also some of the reasons why we might use certain models to maintain some validity. Let's look at a third example. Let's look at this situation where I've got a pulley system which is being used to lift a box. Now, I've got a series of forces involved, and we'll look at these as we go into modelling in more depth in a later unit. But my assumptions for my model here will be that the pulley is smooth, and that means there's no friction on the pulley, that the rope is light and therefore has no mass, and that the rope is also what we call inextensible. I'm interested in a rope that does not have any ability to stretch under load or force. And I'm also going to model my box as a particle. So there's a number of assumptions in this case. Now, my validity will be fairly good here, okay? I'm uninterested in any resistive forces because the box is going to be moving too slowly for their resistance to be a serious issue. Now, the validity is only going to be seriously affected if actually we've got a situation where the effort being put on this side, the force on this side, is actually being dissipated along the length by some elastic nature of that rope. Okay, so one of the key reasons, or the key assumptions here we make, is that the rope is not elastic, okay, inextensible. That means that the force applied at this point of the rope is going to be the same at this point, okay, and also the same at this point, right? So the force is transferred along the entirety of the rope. Another quick example just to show you and look at how these kind of modelling assumptions and the validity kind of interact is this situation where I'm turning a bolt using a wrench. Now, as I turn that bolt and using that wrench, my model is likely to be the wrench is a rod and the bolt is a particle. The key bit of motion, or the place in which this force is being applied, is along the wrench. And actually, in this case, my validity is fairly good because I'm using the wrench. I'm using a wrench as a rod. I've got a rod which is rigid, and that rigidity is obviously also kind of in the design of the wrench. I always want my wrench to be rigid, so it transfers a force, a turning force, which we'll call a moment, more effectively and efficiently. Now, these kind of modelling assumptions, as we say, will have an effect on validity, and that's something we need to be aware of. The modelling assumptions also are a key way of which we're going to have to understand what the assumptions mean, okay? Now, the key thing for this is, hopefully you've got those good notes from that previous slide, you do need to be really, really clear on what each of those assumptions is kind of talking about. When we talk about an inextensible string, we mean that the force is going to be the same along the length of it. When we talk about smoothness, we're talking about something where there is no friction. Okay? When we talk about a particle, we're primarily interested in the fact that there will be no air resistance accounted for in that model. Okay? Please do have a look at the pre-quiz before you start and have a look at the sheet. Any questions, as always, let us know.